Hi, in video 4 on area formula, we did complete one proof of area formula. And one of the key parts was to show that the critical set of the function has image with hn measure 0. And that is called Sard's theorem. It is very much related to the Morse-Sard theorem from differential manifold theory. We gave a proof of the Sard theorem via recycling the area formula on the regular set where the rank was equal to n. But we want to give another proof of this theorem here that avoids the area formula. Look at the statement of this theorem. It has nothing to do with Jacobians or the area formula or the multiplicity function. And it's just so much useful to have a proof of this that avoids all of that. And this proof that I'm going to present is based on very basic covering arguments and only uses the notion of derivative, and that's it. So it's kind of a more intrinsic proof. Okay, we begin by of course, some observation, and that is fix some x0 in the critical set. Then derivative of f at x0 is a linear map from Rn into Rm, but because its rank is less than n, the whole image of this linear map is sum Rk, and after rotations in the image, we can assume that it's just Rk times 0, which is sitting inside Rm, where k is strictly less than n. So it's an integer, non-negative integer in this range. So let me draw a picture of this. You had Rm, and this linear map takes your x0. I mean, your derivative at x0 takes all, the image of that linear map is some subspace with dimension less than n minus 1, sitting in Rm. Again, after rotation, you can assume that this is just some flat horizontal part of it. I have forgotten to bring my charger, so it just motivates me to finish this proof before it runs out of battery. And again, without loss of generality, we can assume x0 is at 0, f of x0 at 0, so all sorts of these simplifications we can do if we want to. Actually, I'm not going to do this particular simplification. So you have x0, and the derivative, the linear map, takes all of this Rn into a subspace with dimension less than n. Now let's take a ball centered at x0. Actually, it's a nice question how to find the center of a circle using ruler and other basic apparatus. Anyway, so the linear map, so there are two maps that are going into Rm. One of them is the original f, and the other one is the linear map df at x0. So obviously the linear map takes, so here's f of x0. The image of the linear map is contained in this subspace. And in fact, it is contained within a ball. So let's write it out. Derivative of f at x0 applied to ball at x0 radius r will be contained in this affine space intersected with a ball centered at fx0, and I claim that the radius will be no bigger than Lipschitz f times r. We know that the derivative, the directional derivatives, for example, by definition, will never be larger than Lipschitz of f times distance of x from y. So here, distance of y, you take any y here, its distance to x0 is at most r. So this will be, the furthest it can go is Lipschitz of f times r. So f, if being Lipschitz, the same Lipschitz constant also works for df, in fact. So we then know how far this can actually get stretched, no bigger than Lipschitz f times. Because now this is a k-dimensional affine space, we can subdivide this image. So derivative of f at x0 of this ball at x0 radius r, the image can be covered by, you can put it into a cube of side length equal to 2 times Lipschitz fr, and then you divide that subcube into n to power k little subcubes. So you divide each edge into capital N many pieces. Okay, sets of, now the diameter of each of them will be comparable to, so let me write this, up to some constants which depend only on k, will be comparable to Lipschitz of f times r divided by capital N. So this is basically the edge length of a cube that contains this whole blue part, and we've divided it into n many pieces on each coordinate axis direction. So there will be these many sets whose union contains that image, and with this diameter size. Okay, how about image of f? Remember, we want to show that image of f is small, not image of the derivative. By differentiability, there exists some delta positive such that, okay, what does differentiability mean? F of y minus f of x0 minus derivative at x0 applied to y minus x0 divided by y minus x0 goes to 0. So there will be some delta such that this will be less than, say, 1 over n. Okay, let's put this 1 over n here. For all y minus x, so such that y is close to x0 by delta. Okay, what this is saying is that this is some element in the affine plane, and well, this actually is in the affine plane because affine plane passes through fx0. So this belongs to the affine k-dimensional plane, and this distance being less than that, it means, so f of y is within 1 over n times r. So this is the biggest this can get is r, within 1 over n r distance of the affine subspace f of x0 plus derivative f at x0 r n. Okay, of course, provided that r is less than delta. Okay. This means that now that we know, okay, so f itself, will be within a thin neighborhood of that affine space. So all fy's will be here, which means the image of f itself of this ball will be contained in 1 over n times r. So let's do this. So r over n neighborhood of this affine space. Well, I have to say the image of the derivative. If I take too big of a thing. Okay. Now, we had that this image could be broken into n to k many subsets of diameter comparable to r over n times Lipschitz. Now let's forget about Lipschitz. And now you're saying that if you move r over n in that direction, also you contain f of b x0r. So you had these cubes, k-dimensional cubes here, add the other directions this way. So you have same counts in k many, and diameter basically the same. So in each side, it's comparable to r over n. So the whole diameter, which is like the diagonal, is also comparable to that. So n many sets of diameter comparable to r over n cover image of f itself. So we moved from covering the image of the derivative to actually covering the original set. Okay, so we fixed one point in the critical set. Okay, and then we said that for a small r, we can do this covering by these many and that many. We repeat this with every other point. So for every x in the critical set, there exists some delta. Well, first we can pick delta less than 1 if you want, and then you find an r. So we only need one r. So there exists some rx positive such that f of b x rx is covered by union of j equal 1 to n to power k many sets. Let's say e, x, and j. So these, of course, depend on the point x. But so here is your, say, critical set, and you keep covering it. For every point, you do this. But this can be too many overlaps here, because for every single one, you do that. But fortunately, we have the Vitali's covering theorem. So Vitali's theorem says there exists countably many of these. So critical set is contained in union of I equal 1 to infinity of balls xi r I. I don't write rxi just for shorter notation. And such that so balls xi and 1/5 of ri, this collection are disjoint. And these are picked among the previous ones. So for every I, there exist sets eij, j from 1 to n to power k, such that diameter of each one of these is comparable to r over n, and f of ball xi is covered by union of eij, j goes from 1 to n to power k. So f of the whole critical set is covered by union over I, union over j of Eij. So j's go from that, and this goes from 1 to infinity. Without loss of generality here, you can assume that C is contained in a cube negative L to power n in the domain. If it's not the case, you can decompose C into pieces, and for each you can assume this. So L is being here some integer. And then also, without loss of generality, you can assume that all these radii you took, because remember you actually wanted a small radius, you can assume all of them is less than 1. Actually, you need this for Vitali covering the uniform bound on the radii. Anyway, what then happens is the following. Let's estimate Hn of f of c. We want to show this is 0. That's the ultimate goal, remember. Up to this scaling factors in definition of Hausdorff measure and whatnot, this will be diameter of Eij to power n. We're computing n-dimensional Hausdorff measure. Sum over I and j. And then this will be comparable to when I do, so each one of them is comparable to R over n. So this will be to power n. But now I first do the summation over j's. How many of these do I have? N to power k many of those. And this will be R to power n over n to power n. And then this will be actually equal to summation over I. This will be n to power k minus little n and summation R to power n. But I can divide by 5 to power n and put it outside, so I'm still in this realm. And this will be comparable. So you had the cube, C is contained in this cube of side length integer, and at every point you have a covering by radius less than 1. So the most this can seep out is, say, twice the size of cube. So this will be comparable to the measure of this cube, negative L positive L to power n. These are disjoint, that's the whole point, because R over 5 are disjoint, they don't overlap, so they at most cover the cube, the doubled cube, and this will be this. Now let's look at this. This is a quantity independent of capital N, and this is a quantity independent of capital N, and we have this one here. And now here comes the whole point that k is strictly less than n. So let n go to infinity. You can do the whole thing with any n to deduce that Hn of f of c equals 0. End of the story. A beautiful proof of the Sard's theorem using only definition of derivative and just the simplest linear algebra you can imagine. That image of a linear map with rank k is inside an affine set of affine subspace of rank k. And Vitali's covering, of course, was a key. There you are, a beautiful proof of Sard's theorem. We will give another proof of area formula where we will use the approximation of function by C1 functions. And in that case, excuse me, we want to use this version of Sard's theorem with this proof so that we can pass to the regular set and ignore the critical set. Let me know if you have any questions, if you see any flaws in this proof. I'm not sure where this proof is written. I don't have a reference, precise reference for that, but it's kind of a natural and standard proof, quite well known. See you in my next video with a new proof of the area formula. Have a great one, and please subscribe if you have not yet, not to miss on the follow-ups. And also note that I put the PDFs of these notes that I take with slight polishing in the subscription. Plus I put some links to other videos that are related to every video. Any comments, any suggestions, any future topics? you wish I cover? Let me know in the comments. Don't be shy. Let me know what you think, and let's move on together. Thanks a lot.